Hi, my name is Alaina, and this is your Math and Science Center tutor tip. Sometimes students have trouble with determining whether molecules are hydrophobic or hydrophilic, so I made this video in hopes of clearing it up. So let's start with the basics. Hydro means water, and phobic means fear, so together hydrophobic means water-fearing. Basically, this just means that these types of substances need help to move through a cell because they do not like water. On the other hand, philic means love, so hydrophilic means water-loving. So these substances are able to easily travel through the cell because they like water. A common example you will see in the science world is phospholipids, and most of the time you will hear this term in relation to phospholipid bilayer. And this phospholipid bilayer is amphiphilic, meaning in one region it is hydrophobic and in another region it is hydrophilic. So if you look in the picture on the slide, the round parts are the heads, and these touch water, so they are hydrophilic. And then the tails are hydrophobic, which is why they hide inside away from the water. So how do we tell whether a molecule is hydrophobic or hydrophilic based on its chemical structure? Well, first off, functional groups can be classified based on their charge and polarity characteristics. Most nonpolar molecules are going to be hydrophobic, and most polar molecules will be hydrophilic. Water is polar, which is why other polar molecules are hydrophilic, because like likes like. So how are we going to determine if a molecule is polar? Well, first off, we're going to have to draw the Lewis structure of the compound. Next, we'll determine the electronegativity difference of the bonds to those of the central atoms. If the electronegativity difference is less than 0.4, we can stop here and just call it nonpolar, so it would be hydrophobic molecule. But if the electronegativity difference is greater than 0.4, it technically could be nonpolar or polar, so we need to find out more information to determine which one it really is. Then we need to figure out the molecular shape, and finally we will decide if the environment around the central atom is completely symmetrical. And then now we have enough information to tell if the molecule is polar. On this slide, I have just pasted a chart that labels the electronegativities of the periodic elements, which will be necessary to determine the electronegativity difference. So you can come back to this slide or take a picture of it when you're working through a problem. This chart just shows you what type of bond a molecule would be classified based on its electronegativity difference. So remember, anything less than 0.4 is considered nonpolar automatically. If it is above 0.4, we need to do further investigation. Here I have a picture to look at for knowing what that molecular shape, aka geometry, would be, and next to each type it tells you whether it is polar or nonpolar. Don't forget to look at whether the molecule is completely symmetrical, because like for instance linear, if both atoms surrounding the central atoms are the same, it is considered nonpolar, but if there are two different atoms, then it is considered polar. Alright, practice time! So first up, let's look at carbon tetrachloride, or CCl4. So first step, draw the Lewis structure. Done. Step 2, determine the electronegativity difference. So chlorine's electronegativity is 3, and carbon's is 2.5. So if we do a little subtraction, we get that the electronegativity difference is going to be 0.5, which is greater than 0.4, so we have to keep going because we still don't know if it's nonpolar or polar. So step 3 is to determine the molecular geometry. So in this example, it is a tetrahedral, but the last step is to decide if they're completely symmetrical around the central atom, which this one is. So based on all of that information, we know that carbon tetrachloride is going to be a nonpolar molecule, which means it is hydrophobic. Alrighty, let's try one more. So we're going to do the same steps as last time, starting with drawing the Lewis structure of dichloromethane. Next, we determine the electronegativity differences. But since both carbon to chlorine and carbon to hydrogen electronegativity differences are above 0.4, we have to keep going because we are still unclear of whether it's nonpolar or polar. So now we're going to figure out the molecular geometry. So CH2Cl2 is a tetrahedral shape. And if we look at the symmetry, this molecule is not completely symmetric because there are different atoms surrounding the central atom. Therefore, dichloromethane is a polar molecule, so it's going to be hydrophilic. Alrighty, and that's it. I hope this was helpful, but if you have any questions, just talk to your professor or visit us in the Math and Science Center.